July 1st, 2025. It was an ordinary night at the Chilean Atlas Observatory until a routine scan flagged something impossible. The object was so strange that experts realized it didn't belong to our solar system. Now, for the first time, NASA's newly released images of 3I Atlas reveal a third interstellar visitor, and with it, a flood of new evidence that could change how we understand our place in the cosmos. But in the chain of alerts, metadata policies, and rapid-fire discoveries that followed, one question lingers. Can we trust what we're seeing? And what secrets does 3I Atlas still hold? On July 1st, 2025, the Atlas survey in Rio Hurtado, Chile, registered an object that defied the usual patterns. The system's automated pipeline flagged a fast-moving point of light, its path out of sync with anything bound to the sun. Within minutes, the data landed in the hands of John Tonry and the Atlas team. The initial alert did not just stop at a single detection. As protocols demanded, the team launched a rapid archival search, combing through images from other Atlas sites and the Zwicky Transient Facility in California. That search paid off. Frames from as early as June 14th, 2025 revealed the same object, faint but unmistakable, already crossing the sky weeks before the official discovery. Each new hit extended the observation arc, tightening the possible trajectory and fueling a sense of urgency in the control rooms. The confirmation process moved quickly. Atlas's Moving Object Processing System, called MOPS, linked the new detection with these earlier sightings, ruling out false positives and instrumental noise. The object's motion stood out. Hyperbolic, inbound from deep space, not following the gentle curves of a solar system wanderer. Within hours, the team reported their findings to the Minor Planet Center, triggering a global cascade of alerts. Telescopes around the world, both robotic and human-operated, were notified. Each observer received a data packet, including object name, discovery date, coordinates, magnitude, and a preliminary orbit fit, following the strict metadata standards that govern every Minor Planet Center circular. This was not just a local curiosity anymore. The world's astronomical community now had a new target, and every second counted. For John Tonry and his colleagues, the night blurred into morning as they fielded calls and coordinated follow-up. The speed of confirmation was unprecedented. In less than 24 hours, the object's status shifted from anonymous blip to candidate interstellar visitor. The observation arc, stretched by those June images, allowed for immediate orbital refinement and a flood of requests for telescope time. Every detail, instrument name, exposure time, observatory code traveled with the data, ensuring the discovery could be traced and verified by anyone who asked. Atlas had done its job: catch the unexpected, alert the world, and hand off the mystery to a global network now racing to unlock the secrets of 3I Atlas. Every discovery in modern astronomy leaves a trail, a chain of evidence that must be preserved from the first detection to the final published result. With 3I Atlas, this process began the moment the object's motion triggered an alert in the Atlas system. The Minor Planet Center, MPC, acts as the clearinghouse for such discoveries. Their notices arrive stamped with a persistent metadata policy, a set of rules that define what details must travel with every observation. Object name, discovery date, observatory code, instrument, observer, coordinates, and magnitude are not just labels. They are the backbone of the global alert system, allowing any astronomer anywhere to trace the lineage of a detection back to its source. Each MPC circular follows a strict format. The header fields are non-negotiable: the object's official designation, the time and location of the observation, the instrument used, and the name of the observer or team. These details are not simply for record keeping, They establish the provenance of each data point, ensuring that every step in the discovery process can be audited and verified. When the Atlas team submitted their report, the MPC assigned a unique identifier linking the new object to its growing catalogue of celestial bodies. This identifier, along with the original observation data, becomes part of an indelible record, accessible to researchers and the public alike. NASA's own data management policies reinforce this chain of custody. Every image released, whether from Hubble, JWST, or a planetary orbiter, carries with it a caption that lists the instrument, exposure time, filter, and processing steps. The agency's scientific information policy requires that all funded data be labeled with the object's official name, observation date, and a record of who captured and processed the data. These metadata fields are mirrored in the archives, from the Minor Planet Center online tables to NASA's own repositories like MAST and the Planetary Data System. The result is a system where every frame, every spectrum, and every orbital calculation can be traced back to its origin, with a clear record of how it was obtained and by whom. This meticulous approach is not just bureaucratic formality. In a field where false positives and instrumental artifacts can easily mislead, the ability to audit the full history of a detection is vital. When telescopes around the world responded to the 3I Atlas alert, they did so with confidence, knowing that the metadata attached to each MPC notice met the highest standards. As new images began to arrive, each one added another link to the chain, complete with persistent identifiers and detailed captions. This is how the astronomical community ensures that discoveries like 3I Atlas are not only exciting, but also trustworthy. Every detail documented, every step open to scrutiny, every image and alert are part of a global, verifiable record. The first images from Hubble arrived in NASA's public archive on July 21, 2025, each stamped with a precise chain of metadata, instrument, filter, exposure time, and the official 3I Atlas designation. In these frames, the object appears as a pinpoint of light, unresolved even through Hubble's powerful optics. At a distance of 277 million miles, the nucleus is too small to reveal any surface detail. But the images do show something more, a faint, diffuse glow surrounding the core. This is the coma, a cloud of gas and dust released as sunlight warms the surface. Careful stacking and contrast enhancement make the coma visible, but its presence is subtle, just a gentle extension beyond the instrument's point spread function. In the days that followed, data from NASA's Lucy and Psyche missions, as well as Mars-based orbiters, added new perspectives. Each dataset carried its own technical fingerprint, exposure logs, processing steps, even the sequence of calibration frames used to reject cosmic rays and background noise. In every case, the nucleus remained a point source, but the extended coma and hints of a tail began to emerge. Especially in images captured as 3I Atlas passed near Mars, the faint tail stretched away from the sun, consistent with dust and gas being blown back by the solar wind. The SOHO and Stereo solar observatories contributed wide-field images, where the tail's structure became more pronounced, confirming that the activity was real and not an artifact of processing. NASA's release presented both raw and processed versions of each image. The raw frames, often grainy and unimpressive to the untrained eye, are essential for scientific verification. Processed images, built from stacked exposures and median filtering, bring out the faint features without introducing artificial patterns. Every enhancement step is logged in the caption, and each frame is cross-checked against independent exposures to rule out cosmic rays, detector artifacts, or background stars masquerading as cometary features. The consistency across multiple instruments and viewing geometries builds confidence. The coma and tail are genuine, not illusions born of overzealous image manipulation. Speculation about the object's nature appeared almost as soon as the images did. Some claimed the features looked too regular, too sharp, or too faint to be natural. NASA's science team responded with detailed breakdowns of the imaging process, pointing to the repeating presence of the coma and tail across different platforms and times. No single image stands alone. Each is part of a chain, corroborated by independent teams using different detectors and filters. The agency's public Q&A posts, as well as statements from outside experts like Karen Meach and David Jewett, emphasized that 3I Atlas behaves exactly as a small, active comet should. There are no unexplained emissions, no geometric shapes, no evidence for artificiality. The morphology matches what is expected for a visitor from deep space, shaped by sunlight and the solar wind, not by engines or alien intent. Every detail in the NASA release is anchored in the metadata: the date, the instrument, the exposure, the processing. These fields are not just bureaucratic formality, they are the foundation for trust. When images show a faint tail, it is because the data, the calibration, and the cross-verification all point to the same conclusion. The features visible in July's Hubble dataset and in the months that followed are the natural signature of a comet in sunlight, not a product of hype or digital trickery. As the images accumulate, each one adds another layer of certainty, linking the visual record to the physical reality of 3I Atlas, an active interstellar comet, captured in the act of shedding its outer layers as it races through our solar system. The path of 3I Atlas through the solar system is written in numbers as much as in images. In early October 2025, the Mars Reconnaissance Orbiter captured a series of astrometric measurements as the comet swept past Mars at a distance of 19 million miles. These data points, gathered by HiRISE and processed at the University of Arizona, were not just another set of pictures, they became the pivot for the entire orbit solution. Mars, sitting far from Earth's line of sight, provided a rare geometric advantage. With the comet viewed from two widely separated vantage points, the team could triangulate its position with unprecedented accuracy. David Farnokia at JPL led the updated trajectory modeling, integrating the Mars Reconnaissance Orbiter astrometry with ground-based and space-based data. The numbers told a clear story. The eccentricity of the orbit, now calculated at 1.016, with an error margin of just 0.001, left no room for ambiguity. This is a path unbound by the Sun, a hyperbolic escape that cannot be explained by any known solar system object. The inclination, measured at 87.4 degrees, placed the incoming trajectory almost perpendicular to the plane of the planets. The velocity at infinity, 26.1 kilometers per second, plus or minus 0.8, stood well above the threshold for solar escape. Each figure was checked against the JPL Small Body Database and the Minor Planet Center's latest updates, confirming the object's status as an interstellar visitor. Before the Mars pass, orbital fits carried a stubborn uncertainty. The error ellipse, stretched along the line of sight from Earth, left a sliver of doubt, a small chance that this was a long-period comet from the Oort cloud, masquerading as something stranger. The Mars-based data changed that. The uncertainty in the semi-major axis shrank to just 0.003 of an astronomical unit. According to Farnokia's post-MRO memo, the error ellipse contracted by a factor of 10, a leap in confidence rarely seen in the field. The probability that 3I Atlas is anything but interstellar dropped to less than 1 in 10,000. For Paul Chodas at JPL, the numbers were decisive. The object's path, as plotted after the Mars campaign, simply could not be reconciled with a solar origin. This geometric breakthrough was only possible because of the unique timing and position of Mars. As 3I Atlas passed near the red planet's apparent location, the angle between Earth, Mars, and the comet reached a maximum. That spread, or parallax, allowed for a three-dimensional fix, an observational baseline that no ground-based telescope could match. The MRO images, faint as they were, became the linchpin in a global effort to secure the object's classification. Each pixel, each time-stamped coordinate, was logged into the NASA Planetary Data System and cross-referenced with the Minor Planet Center's ARC. The result was a trajectory pinned down with a precision that transformed speculation into certainty. With the orbit now locked, the focus shifted to what the object is made of and how it compares to previous interstellar visitors. The geometry and error reduction provided the foundation. The next challenge, deciphering the volatile inventory and physical nature of 3I Atlas, would draw on this secure orbital context, ensuring that every compositional clue could be traced back to an origin beyond our Sun. The James Webb Space Telescope MIR SPEC instrument delivered the most revealing data yet on 3I Atlas, capturing a high-resolution spectrum in early August 2025. The numbers were unambiguous. The coma's dominant volatile was carbon dioxide, not water, a reversal of what is typically seen in solar system comets. By integrating the flux from the carbon dioxide band at 4.26 microns and comparing it to the water signature at 2.7 microns, the team measured a carbon dioxide to water ratio of 7.6 with an uncertainty of 0.6. This is not just high, it is nearly an order of magnitude above the norm for comets orbiting our Sun, where water usually outpaces carbon dioxide by a wide margin. To confirm the result, ground-based telescopes at Keck and the James Clerk Maxwell Telescope collected spectra in the weeks that followed. Their readings, though less precise, landed in the same range. Carbon dioxide consistently outstripped water, with ratios hovering between 6.5 and 8. Even as 3I Atlas swept toward Mars and then back out again, the carbon dioxide dominance held steady. No significant change in the volatile mix appeared over time, or with changing distance from the Sun. This composition stands in sharp contrast to the first two interstellar visitors. 1I Oumuamua offered no detectable volatiles at all, no coma, no tail, no measurable gas. 2I Borisov, on the other hand, was rich in carbon monoxide, with a carbon monoxide to water ratio far above the solar system average, but its carbon dioxide content remained unmeasured. 3I Atlas, with its carbon dioxide-driven activity, carves out a new branch in the family tree. It behaves neither like a typical comet from our own system, nor like its interstellar predecessors. The spectrum hints at origins in a region where carbon dioxide ice was abundant, or perhaps at a history shaped by cosmic rays and interstellar radiation. For the scientists who led the James Webb Space Telescope campaign, the result is a puzzle and a promise, a chemical fingerprint that defies easy classification and demands new theories about how small bodies form and evolve in distant planetary systems. Despite the flood of data from telescopes and spacecraft, the story of 3I Atlas is still riddled with unanswered questions. Even with Hubble, JWST, and Mars-based imaging, the true size and shape of the nucleus remain out of reach. At hundreds of millions of miles, the object is just a point of light, its core unresolved by any current instrument. The coma and tail are visible, but their fine structure blurs into the background, and the precise outgassing rates are still uncertain. Spectral readings, so far, have only scratched the surface. No isotopic measurements have been published, and the chemical inventory is far from complete. One of the biggest unknowns is whether 3I Atlas is experiencing non-gravitational acceleration. For earlier interstellar visitors, such as Oumuamua, subtle deviations in their path hinted at outgassing or other forces at work. For 3I Atlas, the available astrometry is not yet precise enough to confirm or rule out these effects. Teams led by Marco Micheli at ESA and Davide Farnocchia at JPL are sifting through the latest position measurements, searching for any sign that sunlight or jets of gas are nudging the comet off its calculated course. Detecting such tiny shifts requires months of careful tracking and cross-checking with ground-based and space-based data. The next window for major observations opens in December 2025, when 3I Atlas re-emerges from behind the Sun. Large telescopes are already booked for a new round of spectroscopy, aiming to pin down the isotopic fingerprints that could reveal the object's birthplace. The hope is to catch a glimpse of rare molecules, deuterium in water, and different carbon or oxygen isotopes that would set 3I Atlas apart from comets born in our own solar system. Until then, the comet remains a puzzle, its secrets locked away in a cloud of dust and gas, waiting for the next opportunity to be unraveled. Each new interstellar object forces us to redefine what is possible in our cosmic neighborhood. Right now, 3I Atlas challenges our understanding of planetary formation and the boundaries of our solar system. As more worlds pass through, the line between home and the unknown blurs. The universe is not distant, it is arriving frame by frame. Let me know what you think in the comments below.